Hello, we're back with more videos on basic interpretation of derivatives. So as usual, as we go through these problems by now, hopefully you should be able to work some of these on your own. So please hit pause after you read the question, try to work out the answer to yourself, and then check it by continuing on through the video after hitting play. So here we go. We're going to start with this number 62 here. The total cost of extracting T tons of ore from a copper mine is C of T dollars. What does it mean to say that C prime of 2000 equals 100, and why is this a positive value? Okay, think about that. Press pause. Come back when you think you have it worked out. Well, let's think about this a minute. C of T is the cost. T is the tons of ore you make. As you increase T, as you get more ore, that's going to cost more money to get the ore out, more ore out. So C is an increasing function of T, so that would be C prime is positive. So that would explain the positive part of it. Now, what does it mean to say C prime of 2000 equals 100? So this says at the point where you're making 2,000 tons of ore, you're getting 2,000 tons of copper ore out of the mine. At that point, the instantaneous rate of change is 100, what would the units be? Let's see. The units would be the units of C over the units of T. So it would be dollars per ton. So this says right at that point, it's costing us $100 per ton. So in other words, to get one additional ton, the 2,001st ton, it will approximately cost an additional $100. How about this next one? The cost C in dollars of building a house, A square feet in area, is given by the function C of A. What is a practical interpretation of C prime of A, and what are its units? And how about what is its sign, too? Okay, well, let's see. To make sense out of this, C is the cost in dollars, A is the area in square feet. And so if we increase the input, A, by adding a square foot, are we going to increase or decrease the cost of building the house? Well, that's going to probably add at least a little bit of cost to the house, maybe a lot, but at least some. And so that will mean C of A is an increasing function, which means C prime of A is positive. The units of C prime of A are the units of C over the units of A. So that would be dollars per square foot. Okay, so what is the practical interpretation of C prime? It's the dollars per square feet. So at a particular area, this would be how much it would cost to add one more square foot to the house. Additional cost for one additional square foot. Alright, let's keep going. Let's try another one. Suppose that G of T represents the gross national product of a country T years from the beginning of 2000. Suppose also that at a particular time the gross national product is increasing but is starting to lag. What can you say about the signs of G prime of T and G double prime of T? Now remember, when we're asking about the sign of G prime of T, we're asking about whether the original function is increasing or decreasing. Since we were told the gross national product was increasing, that means G prime is positive. But the growth is starting to lag, so that means the original function is growing, but it's growing in a concave down manner. When we're asking about the sign of the second derivative, then we're asking about the concavity of the original function. So the original function is concave down, so G double prime is negative. Continuing on here, for short periods of time, the number N in thousands of compact discs sold by a particular rock group each week is related to the number X of times the group's music video was played on MTV. For a particular type of rock music, N and X are related by some function N of X. What does n of 30 equal 74,000 mean? Why would it be positive? Well, it's got to be positive because this says there are 74,000 compact discs sold in this week if the video is played 30 times that week. So you can't sell a negative number of discs, so that, of course, has to be a positive value for n. And you can't play the video negative number of times either, so the input has to be, x has to be positive as well. Okay. I'm not sure if I said that right. N is measured in thousands already, so n of 30 equals 74,000. That means 74,000, in other words, 74 million CDs would be sold. That's a pretty popular group there if they're selling that much. What are the units of n prime of x? Well, the units of n prime, the units of the derivative, are always the units of the output of the original function divided by the units of the input. So it's the units of n divided by units of x. So that's thousands of CDs per number of video plays. Thousands per showing. What's the sign of n prime and how do you know? Okay, once again, if we're asking about the sign of the derivative, we're asking about the direction of the original function. So increase the input, see what happens to the output. That'll tell you the direction of the original function, and that should in turn will tell you the sign of the derivative. So if we increase x by a little bit, say by 1, we're increasing the number of times the video is played. Well, that should increase the number of CDs that they sell. So that means n of x should be an increasing function, and so n prime of x should be then positive. So it would make sense to maybe n prime of 30 equals 7,000. What does that mean? Well, you know what? I think I'm going to change this a little bit. I think this is a little unrealistic. So let me just make this not be in thousands. And so then that 74,000 would be correct. So now it's just number of CDs sold per times the video played. Okay, so what does n prime of 30 equals 7,000 mean? Okay, well, this says this is the instantaneous rate of change in n in CDs per showing when this number of showings is 30. So this says that if we practically it says if we, roughly speaking, if we sell one additional time the MTV shows the video, if they show it one more time, they'll sell approximately an additional 7,000 CDs. And let's try a different one here. A freezer depreciates at a rate of 18% per year. It was purchased new for $755. Write out a function which gives the value v of the freezer as a function of the number of years since it was purchased. Now, since it's going down at 18% every single year, that's exponential decay, or decreasing exponential function. So the value is the initial value times 1 plus r to the t, where r is your rate of decay. Now, since it's decaying, or decreasing, or depreciating, r is a negative number, so that's negative 0.18. So, of course, 1 minus 0.18 is 0.82. So you're keeping 82% of the value each year and losing 18%. V, of course, is the value that you have, not how much you've lost. So it is 755, the initial value, times 0.82 to the t. Notice if you plug in t as 0, you get 755. That's the initial value. And then as t gets bigger, the value goes down. What's its value after 4 years? We'll just plug in 4 for t and evaluate. And we'll round that off. There it is, a whole bunch of decimal places. and we'll round that off. If you look at the original stuff, really there's only 2 digits in that percentage, so we should probably round off to maybe 2 digits here, $340. How long will it take to depreciate to half of its original value? Well, the original value is 755 divided by 2. Notice divide both sides by 755. It really doesn't matter how much it was at the beginning. What matters is that base, or that rate, which determines the base, and the half here, 0.5. Take the logarithm of both sides, the log of what this allows us to do, use the property of logarithm, says that t can be brought out front as a coefficient as multiplication. And then we can divide both sides by that logarithm, and we get that. You can't combine these into one logarithm unless you change the base, so we're going to leave it like that. And of course you can type that in your calculator. ln of 0.5 divided by ln of 0.82, you get approximately this, which is about 3.49 years. Or if you subtract the 3, take the 0.4927, etc., multiply by 12, you'll convert the fraction part to months, and it rounds off to 6 months, so about 3 years and 6 months. What function represents the instantaneous rate of change in the value of the freezer at time t? I really think, so far, this is pre-calculus. Now, once I have talked about instantaneous rate of change, now we're talking about a derivative. Now we're talking about calculus, so we're doing the derivative of that. Well, the 755 is a constant multiple, so we bring it out front. This is b to the t. You get b to the t times the log of b. That's one of our basic derivative rules. So there's the function. How fast is it depreciating when it's exactly 4 years old? Plug in t is 4 in that formula. It works out to be this. Of course, it's negative because it's going down. It's decreasing in value. So it's depreciating at approximately $68 a year when it's 4 years old. Attach a graph. There's a graph. What kind of window do we need to use for this? Well, the values of input and output are both positive, so we're certainly talking about a first quadrant only graph. So you set both x min and y min to be 0. And we know the initial value was 755. So the top value right here needs to be 755, or maybe just slightly above that, and that graph is not matching because it's going up too high. 755, that's 0.822. Okay, let me go ahead and repair that. So here's Graphmatica. Type in y equals 755 times 0.82 to the power x. And we don't see anything because it's a bad window. Change our window. Start the left at 0, the bottom at 0. The top needs to go to 755. I'll go to 800. And just a little extra. And the right, let's try 20 years and see what happens with that. And there we go. There's a decent looking graph. So let's copy that, paste that in here. Of course, we could do the same thing on our graphing calculator as well. Okay, let's keep going. An economist is interested in how the price of a certain commodity affects its sales. Suppose the price P dollars, a quantity Q of the commodity is sold. What is meant by Q of 15 equals 12,000? Well, it says the input is 15, the output is 12,000, the P is 15, the Q is 12,000. So it says when we're paying $15 per item, 12,000 units of the commodity will be sold. What are the units of Q prime of P? Well, they'll be the units of Q over the units of P. So Q is whatever the quantity is measured in. Could be just a count of items, or items can be measured other ways in cases and ounces. Depends on what kind of quantity it is. But it's quantity units, the number of units of the commodity divided by dollars, really dollars per unit, because that's actually a unit price. So units per dollars per unit. What's the sign of Q prime, and how do you know? Well, we're asking about, is Q increasing or not? Let's see. So if we increase the unit price, the dollars per item, do we increase or decrease the number sold? Well, we decrease the number sold, so Q is decreasing, and then Q prime is thus negative. So what's meant by Q prime of 15 equals negative 2,000? We just explained why it should be negative. And what we see here is this means that a price of $15 per item per unit, the sales, let's just say per unit, the amount of sales is decreasing at an instantaneous rate of 2,000 units per dollar per unit. So in other words, increasing the price by $1 additional per unit will decrease the sales by approximately 2,000 units. Or more precisely, we can increase the price by less than $1. By 1/100th of a dollar, or 1 cent, will decrease sales by approximately how much? Well, we divide the price by 100, we divide the units by 100 as well, so by 20 units. So let's use this to estimate Q of 16. So Q of 16 should be approximately Q of 15 plus Q prime of 15. So that's 12,000 minus 2,000 is 10,000. Now someone took a table in this next problem of data concerning the national debt and then approximated the function giving the debt with this function here. So it's got constant term, a linear term, and a couple of exponential terms. So as usual in modeling real-life data, the model does not fit the data points exactly, but it does give a good approximation of the data, at least from 1900 to 1990, is back when this function was made up. And then things may have changed since then. So what a function approximates the national deficit? The deficit is the rate of change in the debt. I mean, if you spend more, the deficit is how much we spend more than we brought in at the national government. That is actually then added on to the national debt, so that's the rate of change in the national debt. So the national deficit is the derivative of the debt. So it's the derivative here. With the derivative of that constant term 0, the derivative of this one's 29. Then this is that constant, e to the 100th x, and then we take the derivative of the 100th x, multiplies by 100, so it moves that decimal point over 2, so it's 20.1891. Plus, similarly, this is e to the x over 10 times 1/10 times the coefficient, makes this 0.044 e to the x over 10. So there's the derivative. What's the instantaneous rate of change in the national debt model in 1940 and in 1985? So in 1940, it was, let's see, and by the way, the units are, I can't really say, but the units are billions of dollars. And of course, x is measured in years. I think it's measured in years since 1900. Okay. All right. So now we put in, yeah, that's right. So then so x is 40 for 1940, and x is 85 for 1985. Plug those in this formula for the derivative, and you can work that out on your calculator. I get these numbers here. So in 1940, our deficit was about $4.2 billion that year, so that we were adding $4.2 billion each year to the national debt. In 85, it increased to 71 billion, over 71.0 something billion dollars per year. Now, the amount of increase or decrease in the national budget deficit is the amount of change in the national debt. How fast was the deficit growing in 80 and 89? So that's the second derivative of the debt, or the first derivative of the deficit. So we take another derivative. The derivative of 29 is 0. And again, this is basically the same with this decimal moved over twice here and once here. And so there is the formula for the rate of change in the national deficit. And then plug that in 80 and 89, and we get these values here. $11.5 billion per year, per year, and in 80. In 1989, it went up to $28.8 billion per year. Okay, and you can do this numerically on the calculator as well using those things. All right, let's try something else here. For short periods of time, the number of hats sold by a particular retailer each week is related to the number X of times the company's billboards are displayed around town. Let N represent the number of hats sold and let X represent the number of billboards displayed. What does N of 5 equal 250 mean? It means if you have 5 billboards displaying their ad, there will be 250 hats sold. What are the units of N prime of X? They are hats per billboard. N units over X units. What's the sign of N prime of X, and how do you know? It'll be positive because N is an increasing function. Because we know if we increase X, we increase N. In other words, if we increase the number of billboards, we should increase, or at least not decrease, the number of hats sold. If the billboards are effective, then certainly we're increasing the number of hats sold, so the derivative is positive. If the derivative of N at 5 is 40, what does that say? Well, it says at the point where they're displaying 5 billboards, the instantaneous rate of change in hats sold is 40 hats per billboard. So if you increase one billboard, say from 5 to 6, that should increase the sale of hats by approximately 40 more hats sold than we had before. We can use this to estimate N of 4 and N of 6. N of 6 is approximately N of 5 plus N prime of 5. So that's 250 plus 40. That means we had sold 290 hats, at least approximately. But N of 4 would be N of 5 minus N prime of 5. We would have done 40 less than the 250, which is a total of 210 hats. Now further suppose that N double prime of 5 equals 4. In this case, is your estimate for N of 6 too high or too low? Well, N double prime is positive. That's the main thing here. Means the function N is concave up. But now wait a minute, it's also increasing. So we have an increasing concave up function. Now, the original function is increasing concave up. The estimates we gave weren't for following the function, they were for following the tangent line. And if you have an increasing concave up function, the tangent line is below the original graph. So our estimates are actually too low, okay, for the stuff in the future. So N of 6, we're estimating that too low. It should be higher. Okay, number 70. The chief financial officer of a company reported that during the previous quarter, profits continued to increase, but at a slower rate than in the past. And if P of t gives the company's profit at time t, what can you say about the signs of P prime and P double prime during the quarter? Well, the fact that the profit is increasing says P is increasing, so P prime is positive. But it's increasing at a slower rate, so that means that rate of growth is decreasing. So P prime is positive but decreasing, and P double prime then is negative. So ultimately, P prime is positive, P double prime is negative. Okay, let's try another one. The average worldwide crude oil price in dollars per barrel during February, March, and April of 2006 can be modeled by the function P of t equals 0.12 t squared minus 1.6 t plus 59.5. It's a quadratic polynomial function, where t is the number of weeks after January 1, 2006. What was the unit cost of oil on the 11th week of 2006? Well, that's just P of 11. So you just plug in 11 there, work that out. Use your calculator if you want to, do it by hand. Either way, you come up with 56.42. So, at the 11th week of 2006, crude oil costs $56.42 per barrel on average around the world, assuming this model is good. Use the model to find the instantaneous rate of change in crude oil prices after the 11th week or at the 11th week of the year. Be sure, let me say at the 11th week. What does this mean? So the instantaneous rate of change is a derivative. So we take a derivative of that. It's a polynomial, so it's easy. The last part's 0. The derivative of the next part here from the right is negative 1.6. And we get 2 times 1.12 is 0.24 and t to the first. So you get 0.24t minus 1.6. That's P prime of t. The instantaneous rate of change right at the beginning of the 11th week is you plug in 11 in there and you get 1.04. Technically speaking, that's the instantaneous rate of change at the beginning of the 11th week of the year. Well, yeah. Actually, 11 is the beginning. Let's say that's really at the end of that week. Okay, let's try another one. A company is marketing bottles of oil. The amount that they are willing to supply to the market is dependent on the price they can get per bottle. They have determined that the following function closely approximates how many bottles they are willing to supply as a function of the price per bottle. S of P is 8,000 times e to the 0.45p minus 2. What are the units of S prime of P? Well, they're the units of P here divided by the units of the S here. So, I'm sorry, backwards. The units of S divided by the units of P. So S is the number of bottles that they have, and P is the dollars per bottle. So it's bottles supplied, and it's dollars really per bottle. It's really unit price there. So the units are bottles per dollars per bottle. What's the sign of S prime of P? How do you know? Well, sign of S prime is going to have to do with the direction of S. If we increase P, the dollars per bottle, they're going to be willing to supply more. Now remember, the supply function describes the seller, the producer. So collectively, the producers are going to be more willing to supply bottles if they get a higher price for their product. So S is increasing, and S prime then is positive. So in general, the supply function is always increasing. Demand, on the other hand, is decreasing. What is the lowest price at which the company is willing to supply any oil? Okay, so I guess we could set this a couple ways you could do it. You could theoretically you could set it at 0 and solve for that. Anything above that. In fact, you can really only get the lowest amount you can actually produce is 1 bottle. So you could also set it at 1. Here I just did greater than 0. And did it that way. So we take the formula and set it greater than or equal to 0, divide by the 8,000 to begin with. That turns out to be irrelevant. So we do this part right here, subtract or add a positive 2. Then we take a logarithm of both sides, gets rid of the e to power, just leaves the power, 0.45p. And then of course that gives us a of 2 on the other side. Solve for p by dividing, and we get log of 2 divided by 0.45. That works out to be approximately 1.5403. So at about $1.55 is the least their amount they're willing to pay. So if you did this with dollars and cents, or round off the nearest cent, $1.54, you'd find out there's not enough of that. But $1.55 per bottle, they will do some. What is S of 2.50, and what does this mean? Just plug it in the original function, which I did right here, work it all out, use your calculator. 86,642 bottles will be supplied, or they'd be willing to supply that if they could get $2.50 a bottle. What is S prime of 2.5? What does that mean? You take the formula for S prime, which we just worked out right here. Okay, hopefully follow those steps. And that's going to be S prime of P in general, reduces to this, 3,600 times e to the 0.45p. And then S of 2.5, plug in 2.5 in place of P, and work that out. It approximately is 11,088, let's say 11,089. So at a price of $2.50 per bottle, $2.50 a bottle, the company is willing to supply it's willing to supply an additional 11,089 bottles for a $1 increase in price, or an additional, let's scale it back to a penny, divide by, let's say, 100, additional 111 bottles for an additional cent per bottle. Okay. Okay, we got a couple more here. The position of an object moving in a straight line is given by S of t equals t cubed minus 3t. So it's like you have a number line that this thing is running up and down the number line. And the position as on the number line, the coordinate, x coordinate or t coordinate, is given actually the s coordinate is given in meters there, and t is measured as a time value in a second. And we're going to assume that time is non-negative, so it'll start at 0 and then go on into the future. So where does it start? Well, it starts at t equals 0. If you look when t is 0, s is 0. So it starts at the origin, and then it starts taking off. Does it always go in the same direction? Does it turn around? What does it do? Well, Find the velocity function. Velocity is the derivative of the position. So we just take the derivative of that cubic polynomial and we get 3t squared minus 3, or in factored form, 3 times t plus 1 times t minus 1. So notice the velocity is 0 when t is negative 1 or when t equals 1. So if you're between those two, let's see, if you're bigger than 1, both those factors are positive, and so where it's accelerating once it gets past 1. Between negative 1 and 1, one of those factors is negative and the other is positive. So in fact, the velocity is negative. So between 0 and 1, it starts going backwards. In other words, in the negative direction on the number line. And then at time t equals 1, then it turns around and starts going in the positive direction and stays going in that direction forever. Okay, let's find the acceleration function. Acceleration function is the derivative of velocity, or the second derivative of the position function. So we just take another derivative and we get 6t. Find and interpret the position at t equals 9. At t equals 9, let's see, you can plug in the original formula here, 9 cubed minus 3 times 9. That turns out to be 702, and that's meters, is the position. So it is 702 meters in the positive direction of the origin at the time t equals 9 seconds. What's the velocity at t equals 9? Take the velocity formula here, 3t squared minus 3, plug in 9 for t, and that's 240 meters per second. So it's moving in the positive direction with the speed of 240 meters per second. That's the speed. How about the acceleration? Again, we take the formula we came up with for acceleration, which was just 6 times t, and t is 9, so 6 times 9 is 54, so it's 54 meters per square second, or it's meters per second. So the speed is increasing by 54 meters per second each second. When is the velocity 0? Already said that, t equals negative 1 or t equals 1. But we already said t is a positive number, or 0. So really it's only 1 second. What happens then? At this point, the object changes direction. It starts going from the negative from the negative direction to the positive direction. Find the position when the velocity is 0. So again, velocity 0 is t equals 1. So plug that in s at negative 2. So it's in the, you have this number line here that's along your road or whatever it is, or the path, and the particle or whatever it is that's moving is 2 units in the negative direction from the origin at time t equals 0. So that's where it starts. Okay. And then it turns around. That's where it gets to at that point, and then it turns around and goes back in the positive direction. Find the acceleration when the velocity is 0. So if we plug in that same value of x equals 1, t equals 1 into the acceleration formula, we have 6 times 1 is 6 meters per second square, meters per second per second. How do we interpret that? At t equals 1, the acceleration is 6 meters per second per second. Also notice that the acceleration is positive for positive values of t, which is all we have. So it's accelerating in the positive direction. So even though it starts going in the negative direction, it slows down as it goes that way, and then turns around and becomes faster and faster in the positive direction after that. Draw graphs of the position, velocity, and acceleration curves. Just graph those 3, and there they are. Here's the part of the cubic position curve, the quadratic derivative curve, and the linear second derivative curve. and we'll pick up there in another video.